Okay, it is 10 o'clock on the dot. We're going to go ahead and get started. Um, Let me play the slideshow. Okay, so hopefully everybody saw the messages from yesterday. I have graded your second exam. Everybody did very, very well. I don't know that there's any super revelatory comments I can provide to the class as a whole. Uh, you can see here the problem breakdown. But again, everybody did fairly well. It's kind of hard to throw curveballs for a doubly reinforced beam because it's just, you just analyze the beam and whatnot. A couple things maybe with the T-beam. The T-beam you were to treat as a single cross section. So because there was two webs, the width was 6 inches and not 3. The D distance was halfway between the steel layers. So some of you use 17 inches, some of you use 19 inches, but it was 18 inches. Other thing was on the shear. The shear problem 8, I guess, or the last problem. I was surprised a lot of people didn't factor the loads. It was a dead load of 20 kips and a live load of 30 kips. You have to factor those. So 1.2 dead plus 1.6 live. Other than that, I don't know that there's any really major comments. You all did very, very well. Now, homework 7.1 is due. That's the one on the effective moment of inertia. I'm hoping that by now that we have exams completed in both concrete and steel, the only 2 exams we have left in either of those classes are the final. So I'm hoping by now we can start getting into a pretty regular routine where every day we have homework in concrete and homework in steel due. I know we had some interruptions there because we had the exams. I wanted to give everybody a break, but now everything should be pretty straightforward. So with that, let's get into our topic of discussion today. We're talking about deflections still. So let me sort of recap what we did on the homework and what we left off with. All right, so I want to start off by looking at this formula. This is the formula for the effective moment of inertia. Remember, the reason that we use an effective moment of inertia is because when we have a beam that's subjected to load, we have some of the beam that's cracked and some of it that isn't. So instead of using the 2 extremes, either the gross moment of inertia or the cracked moment of inertia, we use this value IE, which is sort of like a weighted average, like somewhere in between, because some of the beam is cracked and some of it isn't. Now, I want to look at this formula for a little bit, just to make sure everybody's clear on a couple things. So this formula is a function of 4 quantities, of 4 terms. It's a function of the gross moment of inertia and the cracked moment of inertia. And it's a function of the cracking moment and the applied moment. Now, of those 4 terms, 3 of them have nothing to do with the load on the beam. The IG, the ICR, and the MCR. They don't have anything to do with how much load is on the beam. The only thing that is related to the load on the beam is MA. Now, on the homework and on the example that we did in class, I just gave you the MA values. So if I give you an MA, how do you compute IE? And the reason for that, and the reason for what we did last time and what you did on the homework, is I just wanted everybody to feel comfortable with computing IE. I want that to be a pretty straightforward plug and chug calculation. But now, today, I want to talk about MA and where that value comes from and how that we handle that. Now, the red bullet here, which is arguably one of the most important observations with IE, and I'll admit it's a little difficult to interpret with the way this equation is formatted, but build yourself a spreadsheet, build an Excel spreadsheet, and start playing around with this. And what you'll find is that as the load on the beam increases, the value of IE decreases. And we might open up an Excel sheet here in a second and just play around with that, maybe with the values from our example today, just to show that. Now, it would also make sense from a physical standpoint. I mean, think, as the amount of moment increases, the more the beam wants to crack, so the IE should decrease. So that should make sense from a physical standpoint. But what becomes challenging and what becomes tricky is how we handle the loads on the beam and how we handle what I'm calling staged loading. Okay, so for what we're talking about here, I just want to keep the example simple, and what we're going to talk about for the next couple slides is just a thought experiment, just a conceptual example. So I got here a beam, and let's say that this beam is going to be subjected to 3 loads, like a load 1, load 2, and load 3. Now the important part is we're going to assume that each of these loads are placed on the beam one at a time, okay? So we'll start off putting load 1 on the beam, then we'll put load 2 on the beam, and then we'll put load 3 on the beam. And so the beam will experience different stages of loading, and that's hence the term stage loading. Now, from the last slide, and just from a physical standpoint, it should make sense that as we start applying those loads, the value of the moment of inertia will continue to decrease. And why that matters is because of our deflections, okay? So let's take a look at this from a straightforward standpoint. So, okay, so right here. So I have the beam, and it doesn't have anything on it, and so let's follow the sequence of loading, okay? And so like I said, the beam experiences loads one at a time. So we'll start off putting load 1 on the beam. You should see on the slide that it's sort of animated on there. So the first thing the beam sees is load 1. So the applied moment, so look over here on the left, you can see the calculation that I'm going with this. So the applied moment would be the moment from the first load, and so the deflection would be the deflection from the application of the first load. Okay, and so the next thing that I do is I put the second load on. Okay, and so then the second load applies. Now this is a really important point to observe. Okay, the beam does not see load 2 by itself. It sees load 1, and then it sees load 1 plus load 2. You keep adding the load on top of it. Okay, so the applied moment is the applied moment from 1 plus the applied moment from 2. And the same thing with the deflection. The deflection is not the deflection due to load 2. It's the deflection of load 1 plus load 2. And that's the kicker. So when I apply load 3, the final load, the moment is from all 3, and the deflection is from all 3. Okay? So the important takeaway is that each stage of loading is going to have its own IE value because it has its own MA value, and loads 2 and 3, they never act on the beam by themselves. It's always load 1 and load 2, and load 1, load 2, and load 3. Those 2 loads are never on the beam by themselves. They're always applied on the beam with something else. Okay? So hopefully that concept kind of makes sense. Again, if you ever have any questions, just throw them in the chat, or you can use your audio and shout them out. No worries with that at all. So again, the beam never sees load 2 and load 3 by itself. But as a structural engineer, you might be interested in, well, what is the deflection caused by just load 3? Okay, like what do I know how much load 3 deflects the beam? I mean, think. As you apply the load, the loads are going to, or the beam's going to deflect. So load 1 is going to cause the beam to bend down a bit. Load 2 is going to cause it to bend down even more, and load 3 is going to cause it to bend down even further. What if I just want the deflection from load 3? Well, the problem is I can't compute that directly, because as I apply the load, more of the beam starts to crack. See, this is a problem we don't encounter in steel design. In steel design, the deflections are a lot easier. But in concrete design, because the beam experiences cracking, you can't just compute the deflection of load 3 by itself just by looking at load 3, because those other loads are causing the beam to crack. But what you can do is you can follow the effects of stage loading. So what you can recognize is, if I go back to the previous slide, well, I know the deflection at the end of stage 2, and I know the deflection at the end of stage 3. So the difference between these two is how much the beam deflected once I put that third load on there. So the deflection due to that third load is equal to the deflection from stage 3 minus the deflection from stage 2. And you might be thinking to yourself, okay, I kind of get what you're talking about, Dr. Mike, but why are you talking about this? Why are we talking about all these different weird stages and all these weird loads? The reason that all this stuff is relevant, and the reason why we're talking about this, is because what we're trying to do, and you're going to see this here in a second, we're going to try and compute the deflection due to live load. See, live load works a lot like this. You never have a beam that sees live load by itself. That doesn't work. The first load that a beam always experiences is, for instance, its own self-weight, and usually dead load goes along with that. So it's self-weight and any other permanent loads that go on top of it. Those are the first loads that the beam experiences. Then you put the live load on top of it. So when you're computing live load deflection, or if you're interested in the deflection due to the live load, you can't just compute the live load deflection. You have to compute the deflection due to dead plus live, and then subtract that from the dead load deflection. And don't worry, when we start doing the example today, you'll see how the numbers shake out, how the dead load deflection actually changes from one stage to another. Now, the first thing that we're going to occur, and this really isn't going to matter a whole lot today, but it'll matter a lot on Friday. First, what we're going to do is consider immediate deflections or instantaneous deflections. And what I mean by that is, here's my beam, I put the load on it, what's the deflection right after I put the load on it? Those are immediate deflections. Sometimes they're called immediate, sometimes they're called instantaneous. It's the same thing. The way that concrete behaves, and this will be something that we discuss a little more on Friday, but concrete behavior changes over time. In other words, if I have a beam and I put load on it and I let it sit there for 5 years and I come back later, that beam will have deflected more after 5 years than it would have on day one. Concrete's properties tend to change over time. It tends to undergo things like creep and shrinkage and whatnot. And creep, which is one of the big ones, causes the deflections to change over time. But for now, I don't really want to worry about that. I just want to keep it simple. Now, again, the live load's always applied after the dead load. So you can sort of think of live load as stage 2. So if you want the deflection due to just the live load, you have to take the deflection from stage 2 minus the deflection from stage 1. And again, the numbers in our example today will bear that out. Now, you might ask yourself, well, why do you care? Why do you care about just getting live load deflection? Why don't you want all of it? Well, the reason why is twofold. First, if you open up the ACI spec, you will find that deflection limits tend to be a function of live load, not dead plus live. So for instance, today, we're going to have an immediate deflection problem. So if you look here, this is a table from ACI spec, and you'll see these are maximum permissible deflections in supporting elements. So I'm going to look at these first 2 rows. So I have flat roofs and floors. So we have different deflection limits, whether or not we're looking at a member on the roof versus a member on the in the floor. And I think that would make sense from a user standpoint. Like let's take the engineering building at Marshall. I mean, the beams in the building, the floor beams that are supporting us as professors and students and office workers and janitors and whatnot, those beams experience different effects than beams on the roof. So naturally, we wouldn't treat them the same. But if you have a roof member, you take your deflection due to the maximum of whatever your live roof load is, your snow load, or your rain load, and you compare that against this maximum limit. For floor beams inside the building, we just take the immediate deflection due to the live load and we compare it against its limit. Later on, we'll look at long-term deflections compared against these 2 limits here, but I don't want to get too far down the rabbit hole with this. We'll talk about these 2 on Friday. But what we're going to do today is we're going to look at this limit because we're going to be looking at a floor beam. Speaking of let's recognize we are computing deflections. So remember, we could use the principle of virtual work. We could use some of these design aids. We're going to be using these design aids today. So I have here an image below. This should be familiar. For instance, the maximum moment, WL squared over 8. By now, everybody should be very familiar with that. What we're going to do is utilize this formula here. This formula is the formula for maximum deflection in a simply supported beam with a uniformly distributed load. A couple of things about this formula. Number 1, don't forget your unit conversion factor. We will typically keep our units in this particular format. So our loads will be in kips. We'll usually keep our member lengths in feet. So our distributed loads will be like in kips per foot. But our E values will be in KSI and our moments of inertia will be in inches to the 4th. So we got to throw in this unit conversion factor to get from cubic feet to cubic inches. So that's my first point. My second point is I want to be crystal clear on this because this is going to affect your homework assignment. This formula only works when you have a simply supported beam and a uniformly distributed load. If ever your loading condition changes, this formula does not work. So you're going to have to use a different expression. And remember, if you go to Blackboard and you go to Supplement 1 in course content, you'll see all of the formulas for these different cases. With that, I kind of want to just get right into an example and have this be our focus of today's lecture. So I have a beam and it's projected live load. We're going to assume that self weight, so we don't have to worry. You couldn't compute it anyways because I didn't give you any of the dimensions. But let's take a look at the problem. So we have determined the immediate live load deflection of the beam shown. So what we'll have to do ultimately is to I'm going to send a message in chat. I've been having some intermittent internet connectivity issues, so just bear with me. So apologies if my screen cuts in and out. If you need me to repeat anything, please let me know in chat. So we're going to go ahead and just get into this example. Again, for a simply supported beam, uniformly distributed load, here's our moment, here's our deflection. So these will be formulas that we can use pretty readily. Okay. All right. So here's the problem. And we're going to go through this and compute the immediate live load deflections for this, and we're going to compare it against the ACI limits to see whether or not this beam meets ACI requirements. So you're going to find this is pretty straightforward, and then we'll be able to look at the results here in a second and see how you can actually see the deflections change as the load increases. So let's start off with some basic calculations. First off, I want to look at the moments on the beam. So we have a beam that's subjected to a uniformly distributed dead load of 1 kip per foot and 3 kips per foot for dead and live load. So I'm going to compute these separately. So the moment due to the dead load is WDL squared over 8. So that's 1 kip per foot times 27 feet squared over 8. And so plug and chug, that gives you a moment of 91.125 foot kips. Again, don't forget to square the length. And then the live load is WL L squared over 8, so 3 kips per foot. And that ends up being 364.5 foot kips. All right. Hopefully that's pretty straightforward, just WL squared over 8 for each of these cases. Don't forget, I've also went ahead and included these values. Now, a couple points worth mentioning before we move on. Number one, we've got a gross moment of inertia of 20,000 inches to the fourth and a cracked moment of inertia of 12,500. So whatever we compute for our IE values, It should be between those two values. That'd be 0.1. 0.2, if you look at your cracking moment is 50 foot kips. Your dead and live moment are well above that, so the beam is definitely experiencing cracking. Actually, wait, hold on. I think I skipped ahead. Somebody in chat should have corrected me on that one. This one is, sorry, 273.375. Thank you, Mr. Stratton. I skipped ahead. I apologize. I was looking a little bit ahead. So yeah, it's 273.375. Sorry about that. But I caught myself first, so that doesn't go on the mistake counter. Okay. Actually, let's do that. Okay. So I want to refer to this in staged construction. So let's talk about stage one. Okay. So like any beam, the first load that the beam is going to experience is the dead load. You know, like its own self weight. It's going to experience it first, and then the live load is going to go on top of that. So this is dead load only. So its MA is MD, which is 91.125 foot kips. Okay, so that's important right off the bat. Okay, oh, go away. Okay, so therefore, for stage one, we're going to compute an effective moment of inertia. The idea is that at stage one, there's some load on the beam, so some of the beam is going to be cracked, some of it isn't. So let's compute that a moment of inertia. So it is 1 minus 2 MCR over 3 MA squared 1 minus ICR over IG. I can do a little better than that. This is ICR. And so that equals 1 minus 2 times 50 foot kips, 3 times 91.125 foot kips, squared, and then 1 minus 12,500 over 20,000. And that's all under 12,500. So I'm going to rely on chat here. I want chat to tell me what is the answer to this. Again, this is a formula I want everybody to be familiar with using because we're going to use this, a fair amount. Somebody other than Mr. Stratton on this one. Mr. Stratton already responded in chat. 13160.4. That's what I got. So 13160.4. And what are the units on that? Sorry about that. What are the units on that? There you go. Inches to the fourth. All right. So if you've got that, then your deflection due to the dead load is, and this is our just basic structural analysis formula, 5WL to the fourth over 384 EI. E is the modulus of elasticity of concrete. IE is the moment of inertia we just computed. And then W is our dead load, since that's the load that we're considering. So 384. Let me move this over a bit. And then E, we got E was 3,500 KSI. This is 13160.4. And so 5 times 1 kip per foot. Then this is 27 feet to the fourth. Am I forgetting anything here? I'm forgetting something. There you go. Convert the feet to inches. Exactly right. So this whole thing, or maybe what we could do is we could say, let's just do it like this, 1728. You can do it like that. All right. Now, somebody help me out. What are we getting as an answer for this? I'm going to move this over. Oh, that didn't work out very well. I'll just leave it like that. Somebody got an answer for me? We'll say 3 decimal places. 3. There you go. 0.260. There you go. Inches. Okay. So I'm going to write this over here. The deflection due to the dead load is 0.260 inches. Okay. All right. So now stage 2, dead plus live load. Okay. So now a couple things change. First off, MA is no longer 91. Now MA is MD plus ML, which is 91.125 plus, sorry, let me put my units here, plus 273.375 foot kips. And so when you add these two, you get 364.5. That's where I got that number before. I was jumping ahead. All right. So now that we have a new MA, we have to compute a new IE value. So we have to do that part again. Like I said, we're going to use this formula a lot. So IE is 1 minus 2 MCR over 3 MA squared 1 minus ICR over IG. ICR. So 1 minus, what is that? Oh, sorry, I need a bracket here. This is 3 times 364.5. And this is 12,500. All right. So again, I want to get a little more participation from chat. So somebody else, I'm going to rewrite this one. 12,500. That's a little more clear. So somebody else. So it's not the same folks. You said 12,579.32. I got 12,539. Yeah, okay. That's what I got. I tell you what, we'll just say it's 0.3. That's close enough. All right. Okay. So notice what happened from before. Okay. So maybe what I'll do is I'll use a different color. Look at this value and look at this value. More load is on the beam in stage 2, so more of the beam is cracked. So you go away. So more of the beam is cracked, so the moment of inertia goes down. Okay. Now what we need to do is this. Okay. Now we need to compute the deflection in stage 2. Now I want to show you something. All right. So now we need to compute the deflection due to D plus L. Now, here's what I'm going to do, okay? I'm going to say that that's 5W L to the fourth over 384 EI for the dead load plus 5W L to the fourth over 384 EI for the live load. Now, a couple things. First off, the reason why we're able to use the same formula is because they're both the same type of load. They're simply supported beams, uniformly distributed loads. The moment, no pun intended, the moment that load is something else, like if it's a point load or anything like that, then these formulas don't work and you have to find something else. So that would be my first point. My second point, some of you might be thinking, well, didn't we already do this? Didn't we do this part already? Can't I just use the value from before? The answer is no. No, you can't. You can't use the value from before because it's a different moment of inertia. Okay. Let's just chug it out and let's see. Okay. So let's do this one at a time, and I'm going to write the whole thing out. So and I have a specific reason why I'm doing it this way. I mean, I could compute each fraction and multiply the whole thing by 1728 or try and factor some values out, but I'm specifically wanting to do each one separately. All right. Now I'm going to need some help in chat. I want to do each of these fractions separately. So the first one and then the second one. So let's take the first fraction. That's the part for the dead load component, and then the second fraction is for the live load. That first fraction, somebody in chat tell me what the answer for that one is. All right, I'm getting 0.272. Plus, and what about the second one? There we go. Exactly right. Okay. Now I want to show you something. First off, let's sum these up. Now I can go ahead and sum that up for you. 0.272 plus 0.817 is 1.089. So our deflection due to dead plus live is 1.089. Okay. So that's straightforward, but I want to show you something. Look at this. Let's go up here and look at that. Okay. Look at the very, very top of the screen on the top right. The deflection due to the dead load was 0.26. But look down here below, okay? The first fraction, what did the first fraction yield? The first fraction yielded 0.272. How come we got dead load deflection of 0.26 in stage 1, but 0.272 in stage 2? It's because what the live load did is the live load added more moment to the beam. More of the beam cracked, so that dead load effect changed. So you can't just use the calculation from before. You have to compute a brand new deflection, and this is why. Because under that increased load, the dead load component changes because more of the beam has now cracked, so the beam's gotten weaker. Okay, so don't try and be lazy. It doesn't really work out. Okay. Now, whoop. Now from here on out, it's pretty straightforward. If you want to determine the live load deflection, so we have the deflection due to dead plus live is 1.089, and the deflection due to the dead load was 0.26. So if you want, you can think of it like this. This is stage 2. This is stage 1. So therefore, the deflection due to the live load is the deflection due to dead plus live minus the deflection due to dead load. And so that is 1.089 minus 0.26. And so our live load deflection, actually, let me just put one out. So our live load deflection, subtract the 2, and you get 0.830 inches. And one other thing that we need to do to finish out the problem asked, oh goodness, sorry about that, to check the ACI limit. So if you go back to the problem states that this is a floor beam, okay? So determine if this beam meets ACI requirements and assume that it's a floor beam. Okay. Now, if it's a floor beam, I want you to help me out in chat. So we're looking at that ACI limit table, and we're looking at the top two rows. One is for a roof and one is for a floor. If it's a floor beam, our limiting deflection is L over what? Tell you what, I'll make it a little easier on you here. I'll share. I'll go back and share the screen because we've got time. So here's our ACI limit for deflection, and so we have flat roofs and floors. So our limiting deflection in this case, we're going to be using L over 360, not L over 180. L over 180 is for a roof member. For a roof member, we allow it to deflect a little bit more because it's not going to really have people on it usually, so that's not really a big deal. But for the floors in the building, we have a little bit more of a stringent limit. As that number on the bottom gets higher, the allowable deflection gets lower, so that the higher the number, the more restrictive the design needs to be. So we're going to limit that to L over 360. So let me go back to the notebook. All right, so L over 360. Now, the length is 27 feet, okay? If you just take 27 and you divide it by 360, you're going to get a number, but the units are going to be in feet. We need to take that, we need to convert it to inches. So 12 inches per foot. All right. So 27 times 12 divided by 360. I'm sure everybody can do that. And that ends up being 0.9. So our live load deflection is 0.830. And our limit, or our maximum allowable deflection, is 0.9. So ACI limits met. All right. I'm going to give everybody a second. I want to see if anybody has any questions on this. So our beam meets the requirements. If our beam didn't meet these requirements, what it would mean is we probably need to change the dimensions of the beam because we would want to create a beam that has a higher moment of inertia. So we might need to make it deeper or something like that. We could also possibly increase the concrete properties to create a higher E value. But usually the moment of inertia is what we would try and change in a scenario like this. Excuse me. Any questions in chat? Anything I can do to answer anything? I'll give you all a minute. While you all are coming up with questions, one thing I thought about, one of the things that you notice we never did in this problem, I mean, if you go through it, you don't see any load factors, no 1.2 dead and 1.6 live. You never use load factors when you're looking at deflections. Deflections are a service limit state, not a strength limit state, so no load factors. All right. I'm going to assume everybody's good. I'm going to move. I want to look at the homework. Oh, hold on. Is the ACI requirement table just in the lecture slide? Yes. If you go to slide 7 in the lectures, and I have it uploaded on Blackboard in course content, it's all right there. And these are going to be the same for like the rest of the semester. It's just these 4 limits. Let me go and bring my homework over here. Oh, trying to bring it over to this screen. Okay, so hold on. This is the homework assignment for today, for due Friday. Oh, no, that's not. No, we already did that one. Hold on. Whoops. You already did that one. That's the wrong one. Give me a sec. That's the right one. All right, hold on. That's the right one. Okay. So this is your homework assignment for Wednesday, due Friday. I want to show you something. So it's similar to the problem that we did in class. I just want you to have a little bit more practice with this, but I do want to show you something. So we're going to determine if the floor beam meets the requirements for minimum deflection. So it is a floor beam. For the beam shown, similarly, I gave you an IG, an I cracked, a cracking moment, and so on and so forth. The load shown, we'll assume they include the beam self-weight. Now, I want to show you something right here. So for the point load at midspan, WL squared over 8 and 5WL to the 4th over 384 EI are not going to work. So you need to look up the appropriate formulas. So to give you kind of an idea, hold on. I'll just go to my notebook sort of do that. So here's the problem. So to give you kind of an idea, so your dead load moment is going to be WL squared over 8. That's fine for the dead load moment because the dead load is a simply supported beam uniformly distributed load. However, the live load moment, you are not going to be able to use that formula. You need to go to supplement 1 to look at that. Also, when you're doing your dead plus live, you're going to be able to say 5WD L to the 4th over 384 EI. That's fine. Plus some other formula for live load deflection, and then still, multiply the whole thing by 1728. So if you go to the course content and go to, do we find MA the same way as we did for the example problem? I mean, yeah, so you're going to have like stage 1, MA is MD, and stage 2, MA is MD plus M live. Like that is correct, but what I am saying is that the formula for ML is not going to be WL squared over 8. So I guess the answer to your question is kind of. Like, do you find MY the same way as in the example problem today? This is correct. This is what you got to figure out. It's not WL squared over 8. If you go to the supplements, you'll find it. It's pretty simple. Are there any other questions? We got a minute or two. Are you looking at supplement 1? Yeah, it's looking at the moments. Here, I'll give you as much guidance as I can because I don't want to just tell you. Hold on. So it's supplement number 1, and so it's this supplement. And if you look at the simple beam scenarios, it's in simple beam scenarios. Like figure number 1 is a simply supported, so figure number 1 is a simply supported beam, uniformly distributed load. The one for the point load, it is there. I promise you, it's in simple beam. It's not in cantilever or beam fixed. It's in simple beam over here. I promise you it's there. To do a little bit of looking, and if you like, give it some time, and if you still can't find it, let me know. I promise you it's there. Any other quick questions? All right. Well, I'm gonna go ahead and sign off. Again, that homework's due on Friday, and hopefully for those of you in concrete and steel, we get back into a regular mode where we have like one assignment for each class due every day from here on out. So with that, that's all I got for you in steel design. I'll see you here in a couple of minutes. For those of you that are not in steel design, I'll see you on Friday. That's all I got.